Okay, greetings, folks. Can everyone hear me? If you can't hear me, if somebody would go ahead and check into and send me a text message and relate that you can't hear me, because otherwise we are going to be in trouble. Okay, we've got a lot of FIA students online here, and probably some other non-FIA students, which is awesome. Great. Welcome all you non-FIANs. Okay. Okay, look at this. Joe. Joe gives me a big thumbs up, so I'm assuming that things are going to look great. Now, I have to go and get the thing. I had to change machines really quick, so I am going to hold on. Yeah, hold on for a couple more minutes. So we do know that we are going in the right direction, and so I am going to go and grab my file, and then we should be ready to go. Please give me at least 5 more minutes here. Thank you very much for your patience. Yeah, the microphone is different than the one we had today. I borrowed my wife's headset. My wife is really good, so this headset is going to be not so good. Thank you for your patience. I have to. My wife wouldn't give me the microphone a second time, so we're stuck with what we got. Okay, getting there. Almost ready. Thank you for your patience once again. Okay. Very good. Making progress. Making progress. Making progress. Okay, now you guys should all have a version of Houdini going on your scene. If you're going to try to interact with this, you got to try to go and do this stuff by hand in order to work with the Houdinis. If you don't use Houdini and you don't work with this by hand, I'm afraid you're never going to understand it. So regretfully, you've got to do your best to try to get your hands dirty with this stuff. If you're just looking at the playback and you're hoping that it'll come in through osmosis, you'll get a little bit, but you really got to go and do things a little bit more interactively. Okay. Okay, thanks, Joe. I see. I got your information, and I see that we are good to go. Okay. We have the Houdini screen up and going. We're getting closer, getting closer, getting closer. Okay, so what I'm going to do is I'm going to add this screen, window capture. Okay. Okay. All right, so you guys all see my Houdini screen up? Hopefully you guys all see my Houdini screen. Okay, if somebody isn't seeing my Houdini screen, please go ahead and send me text to make sure that this is definitely working. I don't necessarily see the exact same thing that you guys are seeing. Oh, okay, great. Thank you very much, Emma. All right, cool. So let's get this started. Thank you very much for your patience. Sorry for the delay, everyone. All right. Now, VEX is one of the many Houdini procedural languages. So it's embedded inside of Houdini, and it's really meant to be an alternative for a programming language. It is an alternative to HLSL and GLSL, so it behaves very similar to those languages. It's not exactly the same, but it does look and behave very similar to all of those. It's very, very good for point manipulation. It's very good for creating custom nodes. It's very good for working with particles. And once you start getting into compositing and so forth, it's very good for the compositing. Now, why should you bother learning with Houdini? Well, VEX is really fast. It is super duper fast. It's pre-compiled and it's written in the Houdini natural language, and it's crazy powerful and crazy fast, and you can manipulate almost everything that you want in there. Oh, before we get going, if there's some kind of emergency and you need me to stop, go ahead and shoot me a text message. Now, I'm not able to focus on my text messages all the time, but I'm going to do my best to keep looking over at the text messages on occasion. But if you have any specific questions and they're not an emergency, please go ahead and save them, and then I'm going to have a few minutes afterwards, and then we can go and look at the stream, and I'll go ahead and answer your questions the best that I can afterwards. Okay, now I do have to warn you that the VEX is a bit finicky, and so it does take a little bit of getting used to. But once you do start getting used to it, things start going much faster and get a whole lot easier. So this is where a little bit of patience really pays off big time. Now, I'm going to make the slide deck available off of, I'm not sure how I'm going to make the slide deck available, but oh yeah, I'm probably going to put it up on my OneDrive, and I'll make it available to, I will post it to I will post it before the end of class, so we should be good to go with anything like that. We'll figure out something, or send me a message I will post this on the servers at FIA, but if anybody on the outside wants this slide deck, go ahead and send me email, chris@techartedu.com. That's chris@techartedu.com, and I'll be happy to send you a copy of this slide deck. Okay, so let's go ahead and get things moving along here. So what we're going to do is we're going to create a test environment. So according to this, what we're going to do, we're going to create a whole brand new project. So as always, when we're creating a brand new project, come over here to File and go to New Project. And inside this new project, go navigate your project path to somewhere where you know it's going to be. I know where this home is going to be, so I'm going to leave it there. So I'm going to leave this project name, and I'm going to call it VEXploration. Okay, so you see, oops, it didn't go. VEXploration. Okay, kind of like a pun, exploration on VEX and exploration. You see what I got there? Oh, we got a little bit of nice cheesiness. Okay. Very bad case of comedy there. Poor attempt. Okay, we'll have to work on these more pre-calculated jokes. All right, I'm going to click Accept here. All right, so I've got this blank scene here. I want to just go ahead and save this blank scene off so that I have a good reference here. So I'm going to go to Save As, and then I'm going to hit Job, and then I'm going to type this as Vexploration underscore 1. Oh, why not? Vexploration underscore 1 here. Okay, so now I've got it saved, and it looks like my Houdini projects, my Vexploration project, and the name of this hit file is Vexploration underscore 1. All right, cool. So we're going to start off by dropping in some new geometry. Okay, so Joe says you don't have the ability to see any subscreens in the Houdini. Okay, well, hopefully, does anyone have any problems creating a project? You should be able to create a project on your own. If you're on the outside, if you've never created a project before, very sorry. What you could do is go here to go to File, just go to Set, or just go to New Project, and a window opens up. On the top line, it asks you for a project name. If you just click OK with that, it should create a project for you. Okay, I'll try to avoid any external windows. I can understand why it's not showing, because we're currently only showing the Houdini window, and all those other windows are superfluous. Okay, makes sense. Good to know. All right, note to self. All right, so we're going to create a new object on here. So I'm going to create, I'm going to go ahead and tab and type in geometry. I'm going to add a geometry node, and I'm going to call this testing ground. Okay, so I've got a new piece of geometry called testing ground in here. Let me see if I can change this around so I can share just my entire screen, not just the whole screen. Let me see what we've got here. Okay, boom, 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 boom. Let me see if I can add some kind of modification to that. All right. Image display capture. Okay, display 1. Okay. Whoa, yeah, that would be it. Okay, I think that's working. Okay, so it just spazzed out on you guys. I apologize. I'm going to get rid of the spaz right now. All right, that. Hopefully you guys should all see the Houdini window, and hopefully we have, you should be able to see the subscreens. All right, sorry, once again, user error on my part. All right, so I'm going to drop into my geometry, and so we should end up with a blank geometry right in there. There should be nothing in here. So I'm going to start off by first drop in a grid, and I'm going to leave that by default. Okay, I'm going to zoom out on that. Okay, so now we see a grid here. And so in addition to that, I'm going to drop in a sphere. So I'm going to drop in a sphere SOP. Okay, for the sphere SOP, I'm going to make sure that it's not a primitive, it's a polygon. And we should look like a sphere like that. So let's give it a little bit of scale. So I'm going to make a uniform scale at 2. And let's just go to 4. And let's give it some frequency. So let's give it a frequency of 6. Yeah, so it's got some good juice to it. All right. Now, we also want some extra stuff in here, so let's drop in a Utah Teapot. You go, Utah Teapot? I didn't know that Houdini had a Utah Teapot. Well, it does. So what we're going to do is, we're not going to drop in a grid, we're not going to drop in a sphere, we're going to drop in a Platonic solid. So I'm going to look for Platonic solid. And as I drop in the Platonic solid, oops, I must have mistyped it. Here's my platonic solid, and I'm going to change my solid type to a Utah Teapot. And there we go. And it's looking kind of small. I'm going to make it a little bit bigger, so let's go to 2. Okay. I'm just going to zoom in on it. Okay, now right now it is, you'll notice that it's not really as polygons. If we look at the object type, it will say that it is a bunch of primitives, which are fine, but we need it to be points. So what we're going to do is I'm going to drop a convert sop to it. And now this convert sop changes it to polygons and makes it nice to work with. Okay, now drop in any kind of test geometry that you want. Now, some people like Roberto, some people like the Squab, some people like Crag, some people like Tommy. It's up to you. But hit tab, look for test geometry, and then choose your favorite. You can have the pig head, Crag, we've got the rubber toy, which is also known as Roberto. You can choose the Chab or Twami. And so I'm going to go ahead and use Roberto. And I'm going to change the name so I know he's Roberto, so I don't forget. Okay, we've got Roberto going at us here. Okay, cool. Now, what I'm going to do is I'm not going to, okay, in my notes it says connect all these into a merge sop. I don't want to connect these into a merge sop. What we want to do is connect this to a switch sop. Now, a switch sop allows us to choose one display over another depending on the input that we choose. So if we put the display on the switch, you notice that it bops right there. We see the grid. Now, if we move this dial over to 1, we see the sphere. Now, this sphere might be a bit too big, so I'm going to go over there and make the uniform scale. Make it 2. Yeah, that's a little bit more reasonable. Okay, and then I'm going to change this to the Utah Teapot, which is the 3rd one, and Roberto is number 4. All right, cool. So there we go. So let's go ahead and then add a transform sop. And then let's go ahead and then add a normal to that. Okay, so we've got the transform sop, we've got the normal sop, and for the normal sop, change the normal so that it's working on points rather than on vertices, and then turn off this keep original normal where compute is 0. Turn that to false. And we should have something looking like that. And let's go, I'm going to just focus in, not on Roberto, but the Utah Teapot. Okay, now what we're going to do is we're going to start thinking about VEX. And VEX is done entirely well, it's not done entirely, but from our perspective and what we're going to look at today, it's all done in a wrangle sop. So what we're going to do is we're going to append an attribute wrangle. So if I hit here, attribute, if we go to attribute wrangle right here, this is an attribute wrangle, and if we hit the display on here, nothing changes. Okay, an attribute wrangle allows you, it gives you a little expression window and where you can write your VEX statements. Now, VEX statements. Now, VEX statements don't necessarily have to be very big. In fact, we're going to keep it nice and short today, just for simplicity. However, this little window is what we can do, and we can choose, we perform this VEX expression over points. We're going to leave it at a point, but we can also choose the entire object, or we can do it over primitives. Now, the Utah has a lot of primitives. We want to find out how many primitives it has. We have I, and it's got about 1,600 primitives, so it's got a lot. Now, a primitive is basically like a polygon. Vertices, well, at every point or the intersection of where points meet, that establishes a vertex. And then you can also choose numbers, which I'm going to leave for now. But I'm going to change this back to points. And so what we're going to do is we're going to perform this VEX operation on every single point. So within the context of the attribute wrangle, what we're going to be doing is manipulating only attributes. Attributes define what our object looks like, what it behaves like. If you have a question of what an attribute is, you might look up on the top tab here, and if you hit plus, and if it's not there, go to Inspectors and then go to Geometry Spreadsheet. And here, on this Geometry Spreadsheet, what we're doing is we're looking at all the attributes of the current object. So here we have all the points, and every point has P for position and N for normal. Now if we hit this little tab over here and select as vertices, and so the vertices here, the only thing that they contain is point information. You know, which point does it operate by? If we click this little button here, we get to look at the polygon information. And so the polygon, there is no other information on here. And then for the details, well, there is no other details. So pretty much what we're dealing with is point information here. I'm going to turn this back to the scene view. And so now we're looking at that. So we're only going to be manipulating, in this context, point attributes. And every single point attribute has to be prefixed by the @ sign. Now the @ sign identifies and tells VEX that the variable that we're using is always is going to be a attribute. So, for example here, let's go ahead and type this: at capital C lowercase d equals at capital N. Now finish the statement with a semicolon. Now the semicolon is different than Python, and that the semicolon tells VEX is that the line is basically finished. And then we don't have to worry about it anymore. So we're going to go. Okay, now all you have to do is tell VEX, okay, go ahead and process this. We can go and process this by hitting Control S to save it, or if we hit Control Enter, then we process this. So we see the teapot has changed shape. Now if we dolly around the object, we see that the object has radically changed color. But since we're orbiting around the object, the object is not really changing any color. So what does this mean? Well, if we defined and looked at here this normal SOP here and display this, and I'm going to turn on the point normals, we see that there is a normal on every one of these points. These little blue spiky dealios, each one of these corresponds to one normal. And they're all pointing off in their own merry direction. But if you were to normalize each one of these normals, so that means is that the sum value of their squared of the red, green, and blue components, they're going to equal 1. Aha, there's a bit of math for you. But needless to say, if you have a red, green, and blue, if you have X, Y, and Z value, those translate right to red, green, and blue. So that's exactly what we're doing here, is we are transferring those normal values to the color. And you'll notice that all of the objects, if the normals are pointed right down the Z-axis, which is blue, the Z-axis takes on a bluish color. If it's pointed up in the Y-axis, you'll see that it's pointed more towards green, and if it's pointed towards the right, which is the X direction, we see that it's more reddish in color. And so that's what we happen to have here. Now things start getting a little bit screwy when we go to this. I'm going to go ahead and hit the template selection template right here, leave that on here. When I go to the transform SOP, and I put a little bit of transform on it, and I rotate it up in the X direction a little bit, we see the teapot change color. Now the coloration seems to stay in the same place, but the teapot itself looks like it's moving along. Yeah, but why is that? Why is the teapot changing color, but it looks like the color stays in one place? The reason for that is because we are transforming the shape before we actually apply the normals to it. So the normals are being applied after the transformation of the shape, so that no matter what the shape is, no matter what its orientation is, it's going to recalculate its normals to be a global X, Y, and Z position. So that's why blue always faces the camera right now, and yellow always faces the top. Now if we were to put a transform SOP at the bottom here, and display that, now if we rotate along the X direction, we see the teapot, it maintains its coloration. Okay, why does it do that? Because in the Houdini chain, we've hit this attribute wrangle and we've changed the point color of all of our points. And now those attributes have maintained so that when we look here, and if we were to go look at the spreadsheet, the normals now correspond to the colors. And so you see their normals now are duplicated into the color slots. And so those change no matter what the transformation afterwards are. Because this transformation is only manipulating the position. This transformation is not manipulating the diffuse color that was set. The diffuse color, once it's been set, it's locked. Okay. Now, if we wanted to change things up a little bit, like I said, okay, instead of making the color the normal, what happens if we make it at P colon? Okay, if we go ahead and hit Control Enter. Okay, so what happened here is that the color now corresponds to the vertex position. So if the vertex has a more Y-dominated place, so that means as tall, it's going to be more green. As it gets more towards the Z direction, it's going to get more blue, and as it gets more to the Y, the X, it's going to get more red. Now if we pre-transform this one again, we see that the color changes, but once again we can see the distribution of colors, and we can almost see the quadrant of where the primary colors are taking over. But we have the position now driving the value of our color instead of the normals. Okay, so you might be asking yourself, okay, well that's all good and fine, I get it. You know, CD, what does that stand for? That means the diffuse color. N, that kind of means normal. Okay, I get it. That's cool. But, I guess P, I guess that goes for position. Okay, I can buy that. So, what about all the other things? I bet there are a zillion other attributes. Well, guess what? There are. It's real easy to forget what these attributes are. A handy way of figuring out what these attributes are is, like, I'm always doing this because I'm always forgetting, that if you drop down an attrib VOP sub, so I'm going to drop in a attrib VOP. Okay, attribute FOP sub. Here we go, attribute FOP. Okay, so here's our attribute VOP. If we double click and go into it, then we go into what's known as a VOP network. And a VOP network is basically like blueprints for VEX. Now, I'm sorry if I'm losing some of you on that correlation, but blueprint is the visual scripting language inside UE4. It's very handy. It works but well. It is really nice. It works great. this geometry VOP, we see all of these things on here. And here's a PV, and that stands for V is velocity, P, that's for position, there's a force, there's the age. And some of these begin to make sense. That if we're dealing with particles, then we're going to deal with life. CD, that corresponds to the diffuse color. UV, well, guess that. That's the U and V variety. N, okay, time. Well, that's the time of the entire network. And how much time inc is how much is incrementing. And if we wanted to look at time instead of a floating point, we want to look at it as an integer, we could look at the frame value. PT num is the point number. Okay, what point number are we looking at? The prim num, what primitive number are we looking at? VTX num, which vertex num are we looking at? And num point means, okay, how many points are there in this entire object? Num prim shows how many primitives, and num vertex shows the number of vertices. So this gives you a kind of a visual clue when you forget what all of these attributes are. Now, but some of you might be looking at the, okay, P, that's fine. Oh, wait, that doesn't say position, that says vector. We say V, well, that says velocity, but that says a vector too. Force, okay, that goes. Age, okay. Now, force, okay, most of these are vectors. Now, you're probably going like, hey, what gives? What's with all these vectors? You know, I'm okay with an integer and a float, but what's a vector? Okay, a vector is a collection of numbers. Okay, a vector can have, you know, technically can have one value, but it's kind of like worthless to worry about vectors of length 1. So we usually deal with vectors of length 2. That's exactly what you use when you have a UV, and that's a vector of length 1. So one of the float values corresponds to the U value, and one of them corresponds to the V value. Now, most of the time what we're dealing with are vectors that are value of 3. That means they're 3 long. And so here we're looking at the normal vector. That means it's going to have an X, Y, and Z component. Now, if we are looking at CD, that's going to be a vector too, but it's going to have a red, green, and blue component. Now, some of these are actually, you're going to be dealing with, they might actually have a 4th component. And on those special occasions, that 4th component corresponds to alpha, which is the amount of transparency. Or if you're dealing with something like position, that 4th value is the homogeneous coordinate, or that's the W coordinate. And so that identifies if this point is actually a physical point or it's just a directional vector. 6 and 1 and half a dozen of another, I guess. But if you don't understand what that means, that's okay. Just in the most case, just worry about vectors. They usually come in 3 flavors. Vector 2s, vectors 3s, and vector 4s. Okay, so use this to identify what your points are and what your attributes are. Okay, I'm going to go up and get out of there. And so let's return back to our attribute pop. Okay, so since we're dealing with vectors, how do you deal with vectors? Well, what you could do is, right now we're dealing with vectors here. We're treating them as entire entities. We're saying, okay, make the diffuse vector equal to the position vector. Now you could make that correspond to, instead, you could do it with indexing. So you could say at CD 0 equals at P 0. Okay, what does that mean? That means the 0th component in this vector, in this case, it corresponds to red. It says red equals the position 0. And in this situation, what is the 0th component? That corresponds to the X component. So we're saying, okay, go ahead and put the X component inside of the red component. So if we go ahead and get rid of this statement here, and then just hit Control Enter, now we can see that this sucker is shaded only to according to the position. And so by default, it's magenta, cyan. And cyan has equal levels of green and equal levels of blue. Okay, that's fine. What's green plus blue? Cyan. Now, but as we're going in X, this value starts to transition into stronger X values, and that means red is coming more into vogue. So as we move to red, so if we were to transform this and move it along the X direction, we start to see it get more and more red. All right, cool. So I'm going to return this back to the original position, and so it's moving along there. So that's one way of transitioning it. Now you could use the channel name instead of the index. So here we have CD, the color diffuse. Now let's suppose we wanted to do this for the, let's just say for the blue channel. So then in that case you would say dot B. So that means is for use the blue channel, and here let's say this equals this would be the second, but this would be the Z. So there, if we hit Control Enter. Okay, now we see that as we go away from the Z direction, it goes to white. And if we were to move it more into the Z direction, it starts to turn more blue. But as it goes away from away from Z, Z becomes 0, and then therefore all we're looking at is red and green, which of course when combined they make yellow. So that's why it becomes more yellow when it moves back into the Z distance. All right, so that's how you can manipulate the individual channels, or you can manipulate them as groups. Okay, so what happens if we were to do this with the position? So I'm going to do @p dot y. So let's play with the y position. Let's try to move our object up. We say y equals, let's just say we move it up 1. So we want it to move up a whole value of 1. So I'm going to hit Control Enter, and blammo! Look at that. The sucker squashes right out there. It flattens out like a pancake. Why? Is because what we have done in here is we've taken the point position of every single point and we made its y value 1. Okay, VEX is doing exactly what we told it to do. It made every point position 1. And if we look under here at our spreadsheet, hey, look at this. Every one of our points now is at position 1 in the y direction. Okay, not too helpful because flat Utah teapots are almost worthless Utah teapots. So let's go ahead and undo this. Let's set it to 0. And hopefully undo what we just did. Okay, great. We got now a flat teapot pointing at the origin. Now that doesn't help us anything. How do we get rid of that? Well, let's just stop manhandling the P direction. They just leave it as is. So I'm going to hit Control Enter with nothing, and there we go. So what do we do about that squashing? Okay, so what we have to do is instead of clobbering and replacing the position value, what we need to do is we need to add to the current value. And we can do that using the plus equals operator. So what is the plus equals operator? So we're going to go at p.y plus equals 1. So in other words, what this actually does, if we hit Control Enter, then we see it moved up a little bit. So what this did was it moved every single vertex the exact vertex value, and it moved it up a value of 1. Now, if we wanted to, let's go ahead and undo this. So if we go at p dot y, if we go minus equals 1, it barfs. So it doesn't like the fact that it used minus equals. Well, what if we use plus equals with minus 1 value here? Okay, so what is the error that it's giving me here? Okay, invalid type, white die, okay, invalid subscript type. Oh, here's the problem. I have a lowercase p. Duh. Alright, it retained this to an uppercase p. Now if we hit Control Enter, there's the object, and he is back to the origin. So let's see if this works if we had done with a minus. Here, Control Enter. Okay, so it stays in the exact same place. So whenever you're just putting in an offset, all you need is the operational thing equals, and then it does relatively rather than absolutely. So if we wanted to, we don't have to use times. We could use, add. We could do this times equal 1. So let's say if we wanted to make it really, okay, so we do it 2. And so our thing's going to move up a little bit. Okay, so it times equal, and then we're going to subtract equal to 1. So what this does here is that we basically scaled our teapot by 2. And then we subtracted a little bit of it, so we just found a way of stretching the teapot. So if we go divide by equals, and then set that to 2, hit Control Enter, there's our teapot, right back, right as rain. Okay, so using VEX in order to offset or manhandle and set an attribute value is very, very convenient. Oh, there is one thing I did forget, and that's comments. And now, what I mean by comment, there's 2 types of comment. You can either use double forward slashes, and you'll see that it turns yellow. That means it's been commented out. So if I go ahead and hit Control Enter, you'll see that he's going to shrink by half. There. He shrunk in the Y direction by half. Okay. But if we don't want to use the forward slash, what we could use is a forward slash star, and then we can have multiple lines, forward slash star, here, and so the whole thing has been commented out in one big old fell swoop. If I hit Control Enter, the whole thing has been commented out. Okay. Great. So that's how you kind of maneuver things around. So, we saw one way of setting a vector attribute. Now, it gets kind of boring setting one attribute at a time. Going to px equals this, pxy equals this, px equals this. Okay, that's like something like C++ programming, and this gets to be a bit boring. So how can you speed things up? Well, you could use something like the set function, and it looks a little bit like this. So we say at cd equals set, and then what we're going to do is for cd is looking for a vector, so let's put it 1, 0, 0. Semicolon. Okay, and I hit Enter, Control Enter. And so basically what we did was say we set the color of every one of our points to 1, 0, 0, which of course means red. So this empowered us to do all 3 at once. Now suppose we wanted to offset its position, and we didn't want to use the set function. Like I said, the set function is a magical VEX function which creates a variable of the type that you're assigning to. And in this case, CD is a type vector 3, so this sets it as a type vector 3. Now, if you want to use a shorthand, you could use curly brackets instead of the C. So I say at P plus equals, and then suppose we wanted to move it up 2, so we say curly brackets, 0 to 0. I'm going to hit Control Enter, and our kettle moves up just a little bit. So what it did is it moved up 2 units in the Y direction. Okay, and that is how you manipulate vectors. You either have to do it on the individual component level. You set them one vector equal to another. For example, CD or at CD equals N. Or you can use the curly brackets. So it's up to you to use what you did. They all mean basically the same thing. It's your choice on what to use, whatever you like. So let's see if this works. Okay, there we go. There's our teapot with the rainbow colors into it. Okay, suppose you wanted to do some math with some vectors. Are you going to have to do it component-wise by component-wise? No, that's kind of like what you would have to do if you're working with things in C, and that's a little bit long-handed. If you wanted to multiply things by a scalar, so let's just say for this P position, we're moving it up 2. So let's change this back to a 1. But I wanted it to move it up 2 units. So what I could do is I could scale this entire vector by multiplying it by a scalar. So I go times, let's say 3.0. Now when I hit Control Enter, it's going to move just a little bit up. There we go. Now if we, the plus equals, if we say 0, Control Enter, it moves it back down to 0. Okay, now you can also do this with vectors in and itself. And so it multiplies according to corresponding components. So if we were to go and say, at CD, equals, let's say the first vector is, we just leave it as is, 1, 1, 1, so that's white. And so the second vector we want to be something like, I don't know, let's say we've got yellow on the brain. So let's make this to maybe 2, 2, and 0.2. Okay, so what this is going to do, it's going to multiply corresponding components. So it's going to multiply 1 times 2, 1 times 2, and then 1 times 0.2. So what do you think this is going to look like? Yeah, it's going to look pretty yellow. Now it's not a pure yellow, because if we look at the color value here, its blue value is actually 0.2. So if we look here, the color value is now 0.2, but the red and the green color are very definitively very large values. Okay, now it is possible to create custom attributes. Now there's a bunch of ways of creating custom attributes. I'm going to go ahead and kind of clean these up, kind of make things a little bit nicer to work with. Okay. Okay, there it is. So the formula for that is you have to tell it what type to make this attribute. Now you can give it a type. Let's just suppose we want it to be a float, just a single float. So we go F, which is a float, we're going to call it offset. We'll just call this one offset. And we say equals some default value. So we'll just say equals to 3. Okay, so what we did now is we created a new attribute called offset, and it's a float value, and we said equal to 3. How do we know that it works? And so if we hit Control Enter, nothing happens because we're not doing anything. When we look at the spreadsheet, we see now offset is a new attribute put in our data set, and it has a value of 3 associated with it. So we do know it's working. So let's go and do something with it. So let's just say, all right, at P plus equals at offset. Okay, all I'm doing is adjusting the old position of P with the new value of P, which is an offset. And so offset is equal to 3. So it's going to move every single component by a value of 3. So we hit Control Enter. So it moved 3 in X, 3 in Y, and 3 in Z. Okay, now I kind of goofed on here. We kind of cheated. 3 in this context is not a float. 3.0, now that's a float. How do we know it's a float? Because it's got the point in it. If it has a point in it, it's a float. If it doesn't have a point in it, it's technically an integer. But, you know, VEX takes care of it for you, but this could create problems in the long run if you allow it to. So I'm going to go ahead and turn this back into an integer. But if we're going to be dealing with an integer instead of an F for float, we're going to change this to an I. Okay, now we're not going to have any kind of problems. Hit Control Enter, and everything now looks good. Okay, now what if we wanted to create a vector? So if we wanted to create a 3 vector, then the value is just V. So V offset equals, and then we have to give it some kind of value here. Let's do curly brackets, close curly brackets. Let's go minus 1.0 in the X direction, 1.5 in the Y, and let's just say negative 2.5 in the Z. Now, if we go P plus the offset, then we're going to offset it by this vector. Oops, it didn't like that. What's my error? It says unable to load shader, failed to resolve. Okay, 331. Expected a dot. Okay, at 331. Okay, so, here it is. Syntax error, my bad. So I said 1.5 dot. This should be a comma. Okay, this should be a comma delimiting it, this vector here. So I hit Control Enter. There it is. So now this teapot has been offset by this vector, negative 1, 1.5, and then negative 2.5. Now for some reason, if we want it to only be a 2 vector, then we have to declare this with the value of U. I don't know why. And so what it's going to do is, since we're only using 2 values for this vector, it's only going to be going into the the X direction and the Y direction. It's going to pretty much ignore the Z direction. So what kind of errors is it? It says invalid literal for type vector 2. Okay, so if we change this to just get rid of it, will it take it? Okay, so it's much happier now. Now that's a 2 vector. Now notice that we're still adding the offset to the position, but we're not dealing with the Z at all. So it probably looks a little bit closer. Now if we wanted to deal with a 4 vector, the value here, instead of U, we would use a value of P. And then let's give it 2 more values. Let's say Z is minus 3.6 and W equals 1.5. What is this going to look like? I don't know. But I think it's just going to move back in the Z direction. So let's hit the Control Enter. Yeah. That's all that happens as it moves back. It ignores what the W value is. But it doesn't go unnoticed. VEX is going to complain here, and it throws up a little warning here. If we hover the mouse over there, it says implicit cast from vector 4 to vector. Use explicit cast instead. So it's complaining. This is a vector 4, and P is a vector 3. It did it, but it didn't do so when it was happy. It was unhappy. It was like kind of grungily doing it and kind of like not doing it voluntarily. So, okay, fine. We'll give it a 3 vector, and now everything should be just fine. Okay, so that's kind of like how you create a custom attribute. Okay, now I do have to throw in a warning. And that is vector attributes like to be set before the performing operator. So if we wanted to create a new vector operator, let's say @foo. @foo equals, and we wanted to put the CD and the CRR and the CG in here. So let's just say foo. I'm going to make sure that this is a vector. VFoo equals, open brackets, @CD dot red divided by @CD dot green. Okay, and now I'm going to put a 1 here, 1.0, and another 1.0. So it's a vector 3. Okay, I'm going to throw a comma there. Hit Control Enter. And it throws an error. It doesn't like this. Okay, so that means is what we have to do is it's got to evaluate this before we're setting it. So in other words, whenever we set a vector like this, we have to make sure that these values have been calculated beforehand. Now, in this case, they've been calculated beforehand, but it doesn't like it. So we have to change this into something more standard. So if we say vfoo equals just 1.0, 1.0, 1.0, we gotta hit that, and okay. Now it's still giving me an error. Why is it giving me an error? It says expecting a parentheses and expecting a thing. Okay, my bad. So here there's a squirrely bracket, and I put a parentheses here. So this needs to be a curly bracket also. Hit Control S or Control Enter, and there's our object. And if we look at foo has 3 values, and they're all 1. And the reason why they're 1 is because we set them all that way. All right, now suppose that you don't want to create an attribute, that all you want to do is create a variable. All right, suppose, like I said, let's look at, float. Now, it uses a different naming convention, regretfully, so this is kind of a pain in the neck. If you're not creating a attribute, you got to use the standard programming language name for these. And if you've done any kind of HLSL or GLSL coding before, you should be familiar with these, and they should not be foreign to you. But in this case, we're going to say float Emma equals 84.76, and we say int gypsy equals 253. But we wanted to make Tom Servo a vector, then we had to say vector Tom Servo equals, and then here we're going to put this as constant 1.0, 0.15 and 0.25. And finish it off with a semicolon. Hit Control Enter, and there we go. And we look and we see there's no Tom Servo, there's no Emma, there's no Gypsy, there's only offset. And the reason for that is because these are now local variables to this particular wrangle. They are not actually attributes. So there's no reason for these attributes or them to show up as attributes in our geometry spreadsheet. We only have to worry about them as local variables, local custom variables. Okay, as a reminder, you do have to worry about sometimes an object is an integer and sometimes it is a float. And the biggest thing is if it's got a dot in it, it's automatically considered a float. If it doesn't have a dot in it, it's automatically considered as an integer. So, if you say something like, let's say int bar equals 1 divided by 2, guess what's going to happen? It's going to round down to the nearest one. We say 1 divided by 2. And if we do a print statement, so we go printf, and what we want to do is, since this is a integer, it's a %d / n, kind of, and then we want bar here. Okay, we're going to hit that. Now, didn't anything happen, but we look here, and I'll look at my Houdini console window, and it says 0. So 1 divided by 2 is not 0, but it's the 0 is the first integer that it encounters. Now, if we wanted to convert this to a float by default, what we do is say 1 divided by 2. If we raise it 2.0, if we go ahead and execute through. Okay, so it's this is called an integer, but now we're transforming it into a float. And so it doesn't like this, so it's going to complain. So what we would have to do in this situation is trans this to a float, and change this guy here to a, instead of a /d or %d, %f, and hit Control Enter, and now we're doing okay. And if we take a look at this, and it should equal 0.5. Okay, cool. So watch out when dealing with floats and integers. It's easy to kind of get confused with each other. All right. Now we can do things kind of relatively. So I'm going to go ahead and clean all of this up. So I'm going to go @cd equals set 100. Okay, so what we're going to do is make this an equal sign. Okay, cd equals to set 100. So if we go ahead and execute this, it's going to look red. There it is, and it returns back to the order. Okay. And so now, what if we wanted to move it up 1 unit? We'd say, okay, at p plus equals, and we're going to create a little vector here, is a 0, 1, 0. So that means we're going to move it up 1 unit in the y direction. And Control Enter. So it moves up. And so if we wanted to offset it by the color, then things are going to look kind of nutty here. So if we say at p plus equals at cd, I don't know, what do you think is going to happen? I have a hunch we're going to get a garbage on our hand. Okay, so it moves off kind of like in a unit in that direction. Okay, so what we could do things is do things relatively. And in that case, what we're going to do is take advantage of the point number and the number of points here. So if, for example, let's go ahead and create a local variable called foo. So float foo equals at point num. Now, point num here is an integer, so we're going to have to remember that it's an integer, but we're assigning it to a float. So what we're going to have to do is do something in order to guarantee that it's a float value. I'm going to hit divide by, and we go at, oops, even that, at the number of points, num point, times, now I don't want to change its value. All I want to do is convert num point from an integer. I want to change it to a float. So all I'm going to do is multiply that guy by 1.0 and leave it exactly the same. So what that does is it converts num point to a float, and then when we have one integer and one float, then it converts the whole thing over to a float. So if we hit Control Enter, everything is going to be copacetic, and then we all have to do this. All right, I'm going to go and take a little break and grab a little bit of water here. But let's take a look at what this expression is doing. Okay, it's going to give the point number. Remember, every one of these points has a specific number. So what are they? If we turn on this little number here, we can see, whoa, they have lots of little numbers on here. And how many numbers are there? So if we go ahead and click on the information, there are 2,100 points in here. So wow, there's a lot of points in there. So this is like 217 out of 2112 points. Okay, that's a lot of points. So what they're doing is we've got this local variable foo, and this is the point number divided by the number of points. So this is 217 divided by 2112. So this is going to be some float value. Okay, what do we do with that? Well, if we wanted to, we could plug that into the thing's color. Now, instead of just going to RGB like we've been doing it, let's nut things around, play a little bit with HSV, just to kind of shake things up a little bit. So I'm going to go vector HSV equals 1, 1.0, 1.0, 1.0. Okay, so there you have is the color white. If you remember HSV space, it's hue, saturation, and value. Hue is 1, saturation is 1, and value is 1 as well. So this one is white. But now, if we take the hue and then we divide it through by foo, now foo is a kind of a gradient. It is now a proportion. So let's just say HSV 0, that means its hue value, equals foo. So that means our hue value is now going to change radically. So let's see what that actually looks like. We say at CD equals to HSV 2 RGB. That's a little VEX function that's given to us. So we're going to transform the HSV variable from HSV to RGB. And let's take a look at what we've got. Okay, so now we know that, remember HSV, it goes from red, kind of like goes from infrared to ultraviolet. Okay, I forgot what those values correspond to, but we notice that the most red values correspond to either the smallest numbers or the biggest numbers. So I have a hunch that these vertices here, if they're going to be closer to red, then these values are going to be closer to 0. So let's take a look at these values. And yeah, they're getting pretty small. And so there's another place where there's some red, and it's way up here. And that's like, okay, you're very near the top. So that means it's the last value. So we're covering the whole gamut here, like going through all of this. Now, using the HSV is usually a pretty good way of getting some very interesting random values and random colors. But using randomness is a whole other issue that I don't think we're going to go into immediately. But if you have any questions about using random, go ahead and feel free to shoot me a comment later on. All right. Now, suppose that we wanted to do some custom channel values. And let's just say that the channel doesn't exist. Suppose we wanted to create a spare channel. Now remember, a channel is any variable that can change over time. That means we can animate that channel over time, or we can have that channel to be procedurally or expression driven. So what we have to do is this. Okay, so let's just say px equal channel mtx. So I'm just going to go ahead and I'm going to change this over here and get rid of all this rainbow color business. And I'm going to say ch, which means for channel. And then I'm going to say mtx. Okay, channel, that's a single float value. And this is coarse square, so it's going to move in a diagonal direction where it goes either from positive to negative. Now, how do we convert this channel to something we can use? When you press this little button here with the slider and a little plus, what it does is it creates any kind of channel or any kind of an attribute it doesn't recognize. It converts that object that it doesn't recognize into a channel. So if we click this, we see that mtx, it goes to 0, but now it is it's been exposed here. So if I go ahead and increase it this way, whoa, it's really fast. So let me move that little value. So there it is. So it's moving along the diagonal, forward and backwards. So it's moving in X, Y, and Z in the same directions. So that's how you create a spare channel. Okay, so let's start playing around, getting things a little bit more wacky and a little bit more interesting. Suppose we've got the rubber toy and here, and let's lay down, oh, I don't know, either lay down the pig or the squab. I'm going to lay down the squab. So I'm going to drop a squab in here. Okay, so we've got the squab in here. And we've got Roberto. And I'm going to get rid of the teapot. So now we're going to deal with Roberto and the squab. Okay, so what I'm going to do is I'm going to turn those objects into points here. So I'm going to drop in a scatter sop. And now I put this, it converts that, okay, we're looking at Roberto. Roberto now has been transformed into, oh, roughly 1,000 points. Oh, let's turn this into 100,000. Okay, now Roberto is being transformed where its manifold is basically a point cloud. Okay, and now let's go ahead and do some kind of operation to those values and sort them according to Y. Notice here that these points are going to have some kind of like random distribution. So if we could turn on the point numbers, oh my God, look at all that. It's all over the place. So if we make this really small, like 10, we see that the point numbers are very random. They kind of like bounce around all over the place. So if we wanted to make that a little bit more constant, what we could do is add a sort sop. So I'm going to go to a tab and then drop in a sort sop. Okay, I've got a sort sop in here, and I say the primitive sort, we have point sort, what we want here is by Y. So sort all these by Y. And so now you see that the lowest points are the smallest numbers and the highest points are the highest numbers. So it's now sorting to Y. Now if we were to just turn the scatter to maybe to 100, we would see that the lowest values are at the ground and the highest values are right up here at the top. Now let's just change this back to 10,000, and then we have a point cloud spectacular. Okay, so what I'm going to do is I'm going to do this. I'm going to do the exact same thing for the squab. So I'm going to select the scatter node and the sort node. I'm going to hit Alt, and then I'm going to drag this over, and it creates a duplicate of it. So then I'm going to release, and then just connect the scatter to the squab. And so now the squab and Roberto each now have 10,000 points. And those points have now been sorted by a Y. So let's hook this up to an attribute sub, an attribute wrangle. Oops, not capture backpack. No, I want an attribute sub. Attribute wrangle. All right, now in case, instead of just having one input, I'm going to put the second input in here. And so now we're looking at Roberto, and the reason for that is because we don't have anything, we don't have any values inside of our VEX stop, so it's going to leave it just as is. So what we're going to do now is play a little bit along with something called the bounding box. Now the bounding box is every single geometry that you ever use inside of Houdini and every piece of geometry you ever use in like UE4, when it goes into the engine automatically creates a three-dimensional bounding box around it. Now, once you start getting into things like ray marching and ray tracing, then you begin to understand why. But just take it for granted that every single object has a bounding box around it that's deformed by the minimum x and the maximum x, the minimum y, the maximum y, and the minimum and the maximum z. So let's change this. So I would say at CD, or the color, equals the relative bounding box. And so I'm going to go rel b box. Okay, there's our explanation of how it accesses it. Now, since we have more than one input, we have to tell it which input to use for this relative bounding box. So we want the 0th one. That means we want to use Roberto, and we don't even want to have to deal with the squab at the moment. So go ahead, and it says take the relative bounding box of the position of Roberto. So hit Control Enter. And now you see we get a rainbow of this. So where it's got the relative bounding box, so the bounding box of each starts at 0, 0, and it goes all the way to 1, 1, 1. But if we wanted to use the relative bounding box of our squab, which is over there, we can change things up. So we're going to change this value from 0, we're going to change that to a value of 1, and then it's going to change it a lot, because remember that our squab is a lot flatter than Roberto. So it's going to look a whole lot different, but it's taking its point values in for its CD values. So it's acting kind of nutty. We're doing a little bit of craziness here. But that's okay. That's exactly the kind of behavior that we're looking for. A little bit crazy, a little bit nutty. Hey, we're at Fire. We can get things a little bit crazy. So let's go even more crazy and add a box. So I'll click here and say add a box up. And I'm just going to put the box up in here. And now, instead of getting the relative bounding box of the squab, I'm going to want the relative bounding box of the box itself. So now we can actually see what this actually looks like. So I'm going to change this to 2. And so it says, okay, use the relative bounding box of the box for this. I hit Control Enter. And now things look at this. Okay, now here's where things might get a little bit dicey. So follow along with me the best that you can. I'm going to put the template on the wrangle attribute. Then I'm going to hit the box, move my cursor over to the window, click in it, and then hit Enter. What that does is it turns on the interactive mode of my box op. And when we did that, we have a transform jack appear. Now you'll see that when we move this transform jack around, that our bounding box is changing, and then the change is going to manipulate the position and the color of Roberto. And it does it for the Y direction, this is for the X direction, and this is according to the Z direction. Okay, so now we actually see this bounding box in action. So I'm going to return this back to the origin. Now, okay, that's cool, but what if we wanted to be a little bit more exact? We're going to get maybe like the point position from 1 rather than using something like the bounding box. Okay, well, we can do that. So what I'm going to do here is I'm going to say at P equals, okay, what I'm going to use is a magical word called Lerp. Now, I know that we don't remember what Lerp is, but Lerp is another word for linear interpolation. So what we're going to do is interpolate from one state to another. And then we're going to use a third state in order to make the transition. So, for grins, let's go ahead and transform Roberto into the squab, point by point, but we're going to create a brand new channel in order to control it. So what this is going to look like is we're going to throw in our Lerp operator. Now remember, Lerp stands for linear interpolation, so that means we're going to linear interpolate from one state to another. And the first state is at P, oops, let me put this in parentheses. At P is the first state, so we're going to take, okay, whatever Roberto's points are, but we want the points that the squab have. So let's take the squab of the squab. So we can't just type in the word squab, we have to designate which input it is. And remember that this is the 0th input, this is the first, second, and third input. So we're going to use the input value of the first, which is the second one actually. So we go at op input 1. Okay, op input says, okay, take the operational input for wherever this is, and which value do we want? Well, we want the P value. So we're going to say underscore P, and we're going to use the value, we're going to create a new channel here called foo. So ch, and open parentheses, open quotes, we're going to call this guy foo, close quotes, close parentheses, and then we're going to close the parentheses for our Lerp and finish it off with a semicolon. Okay, I'm going to go ahead and add a new channel there for foo. I'm going to make sure to hit Control Enter, and nothing happened. Well, why is that? Well, nothing happened because the foo value is 0, and we're using foo as the amount of linear interpolation from the Alberto state to the squab state. So if we move foo from 0, then we're going to see the point thing generally break up, and then it forms the squab. And then we're going to move foo back to 0, and we see it morph back to that. Now this becomes a little bit more apparent when we move the squab geometry up a little bit higher. So we know now we have a real big difference. So now we go here, we see the points dissolve up and then they form the squab dynamically. Now notice that the points still have the coloration that we gave on them from the bounding box. So if we were to go and enter into the bounding box here, the bounding box here would now be able to manipulate this. All right, general craziness and nuttiness. Okay, so I know that's a little bit hard to understand, but what we're doing is we're offsetting the color of Roberto by the position of the box, and then we're interpolating the position of Roberto to the position of the squab, depending on how much we want to do that. Now, if we want to do it halfway, we just have to move foo to like 0.5. And now, this object is half Roberto and half squab. All right, now that's kind of wild, that's kind of funky, but that's intended to be that way. I told you we were going to get nutty. Now, suppose that we didn't want to use a float value. Let's just say, okay, well, I remember in Maya's got these really cool things called ramps. Well, what we could do is we can create a ramp for this as well. So in this case, what I want to try to do is, let's go ahead, I'm going to create a new variable. So I'm going to call it float, and I'm going to call it snafu. What does snafu equal? Okay, what we're going to do is we're going to create a ramp for this. So I say ch ramp. So we're going to make a ramp channel. Okay, now this takes 2 or 3 inputs, depending on the context of which it gets used. So what we're going to do is we're going to put 2 values into it. So the first value going into that is the name of the ramp. So what it quote ramp, close quote. So we're going to call this ramp. And now what value are we going to? Well, we're going to put that proportion value onto it. So it goes from the point number divided by the total number of points. So this is going to look like at ptnum, the point number, divided by at the num points, numpt, times 1.0. Semicolon, and oops, we're going to have 1 parentheses over that. Let me make this a wee bit bigger. You guys be able to see this? Okay, let me go ahead and build this just to make sure I didn't mistype anything. So I can control enter. Okay, nothing happens. Okay, but when we hit the little plus thing, it's going to create a extra channel for us for this ramp here. So we hit plus, and there it is. And here's our ramp now, and now we have a ramp variable. So instead of using foo, let's use a ramp value, or a ramp value, which is in the value of snafu. Okay, I'm going to hit the control enter. And now it looks a little bit nutty. Why? Because it's got a nice steady progression on the point number. So the point numbers that are the oldest, that means that they are the most close to the origin, those stay exactly the same. But the newest points, the ones with the highest value, those are going to be most closely to the squab. Now we can add keyframes in here, like right here into the middle, and then change this value around. And so some of the points are this, and so we can change its proportion as it moves around. So this is dependent on the relative position of every single point with the total number of points in the system. Okay, now suppose, let's see, oh, let's see. We wanted to have the bounding box, and so let's see. How can we interview? Let's get the bounding box in there. We got CD equals relative position of the bounding box. Okay, so now we have this wild looking ramp on here that's controlled by that. Now what happens if we move our box around? So this changes the color of things. Okay, so that moves around, so that's pretty cool. Now, hypothetically, I don't have the notes in front of me. I forgot to put it on here yesterday, but just to see if I'm still thinking and I'm awake. What happens if we still want the proportion of the points to move up from Roberto to the squab, but we want to use the position of our bounding box. Okay, so what happens here if we have here, then we want to have the position of the bounding box. Okay, if we say relative bounding box of P, so what happens if we put the value of at CD in here? And we hit enter. Okay, then things get really nutty. So let's move this bounding box around. Okay, so things really go crazy ape nuts. And if we move things around left and right, things go, whoops, things switch around here. Okay, why is it going crazy ape nuts like that? Well, it's because we're allowing, as we move our bounding box up and down, we get values that are too large and too small. That's going into the positive and the negative direction. And what we could do to go avoid that, we could clamp the values. So let's go ahead and clamp whatever those values coming out of the color are. So let's go ahead and change this and create a new value for a vector. So I'm going to call this vector equals, okay, I'm going to say clamp. Okay, I'm going to clamp my CD value. And I'm going to clamp it between 0 and, let's make it 0.0 and make sure that we're dealing with floats, and 1.0. Oh, I forgot to give it a name, so I'll call vector. What did I get caught? Yeah, clamp me. Clamp me. Okay, and now let's use this clamp me value instead of the CD value here. So clamp me. I still spelled it wrong. Clamp me. Okay. And I'm going to hit Control Enter. Okay, things are changing around, but let's see what happens when we move this bounding box around a little bit. Okay, there we have our squab down below. And so it moves from one position to another. And kind of like floats in a nice... so this makes for kind of like a nice, interesting, dissolving, kind of divesting things. And we see bits and pieces of Roberto. It kind of reminds me of The Thing or The Fly. You know, everyone remember that the film from the 80s with The Fly with Jeff Goldblum? Yeah, I guess I'm dating myself. Oh well, good stuff. Good stuff. Cronenberg. Man, that Cronenberg is a sick mofo. But anyway, before we wrap this up, I wanted to go over one thing. You can create custom functions inside of your wrangle stop. So I'm going to add one more wrangle stop right to the end here just to keep things a little cleaner. And I'm going to call this attribute wrangle. Okay, we've got an attribute wrangle here. And suppose we wanted to create a function. Well, you create a function in here just by the word function. So you have function. This declares that you're creating a function. Yes. And then you have to tell it the type. All right. So suppose you don't know what the type is, or it's a string, or is it like okay? So if it's a let's say suppose we wanted to return a float or an integer. We'll say int, and then we'll just say square me. So square me. This is SQUARE me, and we've got an input value of an integer, and then we'll say val. Okay, there we have, it looks a little bit like that. Return type, there's the name of our function, and here's our input, int val. Okay, then we're going to go ahead and open curly brackets is the start of the function, close curly brackets is the end, and so now let's return, and this is val times val, semicolon. Okay, there's our function. We're just going to return a value. So let's go ahead and say printf. So this is a print statement. And then open quotes, and I'm just going to say, I'm just going to say square me equals, and then we're going to return its value. So we know we're going to be dealing with an integer, so I'm going to say a %d, and then we got to have a \n, or else the system won't know to do a line return. Kind of nutty, but that's just the way it is. Okay, and then we're going to say, all right, return the value of, and then we're going to call it square me. Okay, and let's put in a value of like, oh, I don't know, like 62. Enter that. And so I'm going to hit enter. Okay, nothing happened. Nothing changed, at least visually. But if we go and look here, and it says square me equals 3844. Okay, so it ran through a bunch of times. What would happen, perchance, then if we were to put a float value in here? We'll say 0.76.7654. Okay, now this is a float value. What's it going to do? If we hit Control Enter, okay, it's still doing it. And if we look at the value, it gives us the same thing, but it totally ignores it. It says, okay, that even though this is a float value, and we're returning an integer, it's just going to say, okay, I'm going to cast, and I'm going to turn this float into an integer, and I'm just going to ignore it. But I'm not really going to totally ignore it. I'm going to flag a warning. So if we wanted to change this into dealing with a float, what we would have to do is just say, turn this into a float, and the input would have to be a float, and then we'd have to turn this into a %f, because then we're doing a float. Control Enter, and now everything is fine. Now when we take a look at this, and now we see that the square me now has a more float digital times value. Okay, so that's kind of how you create a function. Now you can go ahead and add more than one parameter. You could say like, okay, let's have it print a string, like right along with it. Okay, so we're going to be returning, or we're not going to return anything. So what we're going to do is we're just going to leave this here, and we're going to do all this. So what we do is we're going to leave this off as a void. So we're not going to return anything. we're going to do all the stuff within the context of this little function and just leave it at that. So we've got square me, and let's put in a string, and a string type is the word string, and we're going to call this, oh, good old foobar. So instead, let's put the string in here. So return, actually we're going to do this, let's go ahead and just hit the print. So printf, okay, we're going to hit double quotes in that, and then we're going to say square me equals, and then %f means that, and we want to print the string value, so the placeholder for a string value is %s. And then don't forget the \n to terminate our line. And then that's the double quotes, parentheses, and finish it off with the parentheses and a semicolon. And now let's go ahead and call our square me function. So just say square me and what kind of value to put inside of it, let's put 83.88, why not? And let's just say, okay, I'm hungry, so let's go bacon! Alright, so what we do is say print square me squared, we didn't return any values here, so what we have to do is add the return values, and so it's val times val, that does the square, and let's return just the string, and that's foobar. Okay, we got val times val, returning foobar, and so we return this. Okay, so hit Control Enter. Uh-oh, and it didn't like it. Oh, wow. It's at 146. It doesn't like 146. Warning, errors are encountered like that. Okay, we got a syntax error. Okay, line 46. Oh, 1, position 46. Okay, this is what happens when you think in Python and you act in VEX. The little separator between our different variable types, our arguments coming into our function, instead of a comma, it needs to be a semicolon. Okay, I hit Control Enter, and there we go, that gets rid of that. And now if we take a look at our function value, it says square me equals this horrible number, and it's printing out bacon. Okay, so as a wrap up, what we did today was we went through some of the basics of how to deal with VEX. Now VEX can actually get very, very complicated. If you really want to know some really complicated VEX stuff, look up Anastasia Apara's stuff. Her stuff is brilliant, and it makes amazing use of wrangle stops. Not easy, but really demonstrates the fullest extent of what you could do with a wrangle stop. But most of the time, I'm kind of a bear of little brain. I like using a wrangle stop for doing basic little one-off thing dealios like this print function, or changing my one attribute at a time. So it's nice and simple. So, but in general, I find myself that once I understand and get over the initial barrier of going, oh, VEX, oh, this is scary, I find myself using VEX a lot, and I find it to be very convenient. And I encourage you to kind of explore and do the same too. Now, before we go, I want to leave it open to see any kind of questions. So if you have any kind of questions, please go ahead and enter them now, and I'll try to entertain you with my crazy-ass voice until I see any questions come in. And if no questions come in the next few minutes, I am just going to probably end this stream. Oh, yes, Anastasia's last name. I'm going to type this in here. Anastasia's last name is O-P-A-R-A. Anastasia Opara. She is brilliant. I guess all I'm going to say is just she's brilliant. I'm going to see if I can get her to come to FIA, or at least come to us, and maybe we can interview her and talk with her and see what she does. She works at EA over in Scandinavia, and I'll see if I can try to contact her and see if she'll come and give us an interview and give us a little bit of an opinion of what she has to say and maybe what her strategies are. I would say that she's probably the best procedural classic artist in the world right now. I can easily say that. But her math and her algorithm are a little bit dizzying. And unless you've studied some computational geometry, most of this stuff is going to leave you in the dark. I would like to try to go and expand on this stuff, but I'm afraid we don't really have time because a lot of this stuff is a little difficult to follow. But I'll see if I can try to get in contact with her and see if she'll give us an interview. That might be an interesting thing. So if not for FIA, then we'll try to do it for the Houdini users group. I think that would be a good guest for us. Okay, any other questions? Okay, I'm going to take a little siesta, a little break here, grab myself a drink. All right, thank you. Thank you very much, Joe. So, I'm going to, if you have any questions, I'm going to, and you don't want to discuss it here, let's say I'm going to go ahead and return the context over to my plate again. And things are going to go wacky ape nuts. Okay, I'm going to turn this off, Houdini, and turn off this display. All right, cool. Oh, I've frozen. What an ugly face. Damn, look at that. Okay, so let's just say that that's that's not working real well. So my camera has frozen. But anyway, isn't that wonderful? The beauties of live entertainment. You never know what kind of wackiness you're going to get. But if you have any questions, please feel free to contact me anytime at chris@techart.edu. Now, I have to admit, I just created this domain last night. And so this email address is fresh spanking new, and I haven't yet hooked it up yet to a mail browser. So I didn't need to hook it up to a mail. So if you need questions and answers right away, I can't comply unless you contact me at my FIA address. So it's just Croda, CRODA at ucf.edu. You can contact me with that. Otherwise, you're just kind of stuck until I can get to the chris@techart.edu.com. But please feel free to contact me anytime. And if you're not from FIA and you want to subscribe to my channel, please go ahead and do so. Or if you like anything, go ahead and like the presentation. And tell me what you want. Tell me what you're interested in seeing. I'm going to spend the rest of the summer, not this week, but next week, we'll be going into procedural foliage. And then once we finish our procedural foliage module, then we'll begin going into procedural landscapes, where one of our artists requested that we go into creating a kind of a procedural cove with some waves floating in and some water into it. And I thought that would probably get a good introduction and give us a good example here. And I'm feeling a little bit nostalgic for old California. So what I'm going to do is see if we can procedurally model Malaga Cove. If you want to see what that looks like ahead of time, you can look that up on email. Look up Malaga Cove. It's the most dangerous spot to surf inside California. And for reasons unto itself. Okay, great. Thank you very much for joining me. Thank you very much for dealing with our technical difficulties. And hopefully by the time we do this again next week, we have all the kinks ironed out. Have a great week. Be safe. Stay healthy. And we'll talk with you later.